Hi there. Welcome back. This is lecture 6 of machine learning from data, and today we're going to be talking about bounding the growth function. Okay, and just to remind you, the growth function is this new measure of complexity that we introduced for a hypothesis set, which views the complexity of a hypothesis set through the lens of a data set. Okay, and the advantage here is that it reduces infinite hypothesis sets to finite collections of dichotomies. And now we're going to analyze those finite collection of dichotomies that can come out from hypothesis sets that we like to use in practice. Okay, now before we get going, let's have a recap of what got us here. Okay. So, we introduced the growth function, which is this way of looking at a hypothesis set through the lens of a data set. And on the top right here, here's an example hypothesis set, and here's a data set. And when you view through this data set, this hypothesis set, which has many hypotheses, is very simple. It just has effectively the ability to implement one function on the data set and on that data set. And a function on that data set is basically what we defined as a dichotomy. It's a way to assign, plus and minus to the data, to the points on this in this data set. So we introduced this notion of the growth function, which says, pick any data set you like, x1, x2, up to xn, and compute all the dichotomies that your hypothesis set can implement on those data points. Okay, and that's a measure of the complexity of the hypothesis set, the diversity of dichotomies it can implement on this particular data set. Now maximize that over all possible data sets of size n. So, go and find the worst possible points x1 to xn that you can in order to try to increase the complexity as much as possible. And then this maximum possible complexity, this maximum number of dichotomies, that can be implemented by the hypothesis set is sort of an upper bound on the complexity of the hypothesis set as seen through any data set. Okay, and this is what we call the growth function. It's the maximum number of dichotomies that a hypothesis set can implement on n points. Okay. And in this lecture, and last time we sort of asked, well, this growth function is at most 2 to the n, and then we showed that, in infinite hypothesis set examples that, it's significantly less than 2 to the n. So the question today we're going to answer is, and we will answer this, definitively, rigorously with a proof, can we bound the complexity of a hypothesis set? Okay, not by the trivial bound of 2 to the n, but by a more useful bound that's polynomial in n. Okay, so we will answer that question. And then the next question that, we posed last time was, is this effective complexity of a hypothesis set, this growth function, is it useful? Does it provide us with an error bar that we got in the finite hypothesis case? Now, we won't go through the detailed proof there, but, you can look in the text, and indeed, a similar probabilistic argument using a version of the Hufting and also a union bound will allow us to replace the size of a hypothesis set with, some version of this m sub h, this growth function. Okay, so just a recap of the 3 hypothesis sets that we considered last time as examples of growth functions. So we considered the 2-dimensional perceptron. Okay, and we saw that with 4 data points, the two-dimensional perceptron cannot implement all 16 dichotomies. Even though in theory, if it was, it's got uncountably many hypotheses and it should be able to do anything you want on just a mere 4 data points, but it cannot implement all 16 dichotomies. So this means that the 2D perceptron is broken. Okay, a deficiency of this hypothesis set has appeared, and it has appeared at just 4 data points. You cannot implement 16 dichotomies on 4 data points. Wow. We thought this is an uncountably large hypothesis set, but it's infantile. It gets destroyed by 4 data points. Okay. The one-dimensional positive ray also uncountably infinite, but that gets broken at 2 data points. You cannot implement all 4 dichotomies on 2 data points. Okay. And the 2D positive rectangles that we considered last time, that's a little more powerful. Okay, it only gets broken at 5 data points. Now, we didn't compute what the growth function is. We just proved that it's broken. Okay, and this shows at least that there's hope. Okay, that some reasonable, infinite, uncountably infinite hypothesis sets do get broken. So this trivial bound of 2 to the n, these hypothesis sets that we considered can't achieve that. Cannot classify a typical data set of size n if n is large enough cannot classify that data set in all possible 2 to the n ways. So there is hope. Okay? There is hope that these hypothesis sets, when viewed through data sets, are not exponentially complex. They may be polynomially complex. Okay? And what will play a key role in the analysis that we're about to discuss is, when does the hypothesis set get broken? Okay? And what we see here is that in all cases, these 3 hypothesis sets do eventually get broken. So let us define a breakpoint. Okay? So a breakpoint is a value of n that reveals the deficiency of a hypothesis set. Okay. What that means is that, for that number of data points, and we'll call the breakpoint k, it's a value for the number of data points k that reveals the deficiency of a hypothesis set. So what that means is that, if you have k data points, there is some dichotomy that cannot be implemented on those data points. So what that means is that, and that's true for any data set of size k. So what that means is that the maximum over all possible data sets of size k is strictly less than 2 to the k. So what that means is that the growth function is strictly less than 2 to the k. And any number of data points for which this holds, we will call it a breakpoint because it's broken the hypothesis set. Okay? It's revealed its deficiency. Okay. And, the goal today is to analyze this beast called the growth function. We're going to come up with a very, very beautiful result. Okay, and in order to analyze this growth function, we're going to gain considerable traction by going back to that combinatorial puzzle we discussed last time, and analyzing that puzzle fairly carefully. So it might look completely unrelated. Man, why? I didn't take a class in combinatorics. Why am I having to analyze a combinatorial puzzle? Well, turns out that it has a very, very deep connection to this growth function guy. Okay. Before we tackle this combinatorial puzzle, let's get some practice with breakpoints and growth functions and dichotomies and all that stuff, because we've thrown a lot of stuff at you, and it's good to get some practice. Okay. So pop quiz 1, I give you a set of k-star points, okay, a specific set of k-star points on which h implements fewer than 2 to the k-star dichotomies. So we introduced a term for that. We say that h does not shatter your k-star point. So what do you know? A, k-star is a breakpoint. B, k-star is not a breakpoint. C, all breakpoints are greater than k-star. D, all breakpoints are less equal to k-star. E, we don't know anything about breakpoints. Okay, so pause the video. Okay, and if you pause the video and are back, or you just continued and are here for the ride, and if you said E, we don't know anything about breakpoints, then you have a good understanding of what it is to be a breakpoint. Okay, so, to be a breakpoint, you must show that, your hypothesis set cannot shatter any data set of size k star. Okay. One data set of size k star is not sufficient. You have to demonstrate that your hypothesis set is deficient no matter what the set of points. Okay. And that's just the definition of a breakpoint. That's the definition of the growth function. Okay, pop quiz 2. Now, for every set of k-star points, you can show that h implements fewer than 2 to the k-star dichotomy. So h fails to shatter any set of k-star points. Okay. What do you know? A, k-star is a breakpoint. B, k-star is not a breakpoint. C, all k greater or equal to k-star are breakpoints. D, all k less than k-star are breakpoints. Okay. And E, we don't know anything about breakpoints. Again, pause the video, and okay, if you answered, A, k-star is a breakpoint, you know what a breakpoint is. Okay, so that's the definition of a breakpoint. A breakpoint is a value for the number of data points, in this case k-star, such that you have revealed a deficiency in your hypothesis set, no matter what set of points you choose. So for every set of k points, it is the case that h cannot shatter that set of k points. Okay. Now, if you observed that once you have found a breakpoint, if your hypothesis set cannot shatter k star data points, no matter how you arrange them, then you cannot shatter any larger value, any larger number of data points, no matter how you arrange them. Then you would have said C, and that's that's great. You have an even deeper understanding of breakpoints. And if you said A and C, then you got it perfect. Okay, because both A and C are correct. Okay, you know that k star is a breakpoint. You also know that everything larger than k star is a breakpoint. Okay, pop quiz number 3. to show that K is not a breakpoint for H, for your hypothesis set H. What do you have to do? So now we're asking you, how will you show that you don't have a breakpoint? Okay, so show some set of K points which H can shatter. Okay, show that H can shatter any set of K points. Okay, show a set of K points which H cannot shatter. Okay, show that H cannot shatter any set of K points. And lastly, show that the growth function m of K is 2 to the K. So to show that K is not a breakpoint. Okay, again, pause the video. Okay, and if you're coming back, okay, and you said A or E, perfect. Okay. So what does it mean for K to not be a breakpoint? By the definition of a breakpoint, it means that you're a breakpoint if you cannot shatter any set of K points. You're not a breakpoint if you can shatter some set of K points. Okay, so that's A. And that's equivalent. If you can shatter some set of K points, then you can implement 2 to the K dichotomies on that set of K points. And since the growth function is the maximum number of dichotomies you can implement on K points, the growth function is 2 to the K, and that's equivalent to the statement you can shatter some set of K points. Okay, so A and E are essentially equivalent from the way we define the growth function. Okay, now if you said B, okay, technically you're not wrong, it's just that it's overkill. You don't need to show such a strong statement that you can shatter any set of K points. So that's not required for K to not be a breakpoint. All that's required is that you have to be able to shatter at least one set of K points. Okay, now C and D, show that, a set of K points cannot be shattered, okay, and show that, any set of K points cannot be shattered. Those are not moving towards showing that K is not a breakpoint. Those are moving towards showing that K is a breakpoint. Okay? So to show that it's not a breakpoint, you must show that you haven't revealed any deficiency in H, which means that H can implement all 2 to the K dichotomies somewhere. Okay? And last pop quiz number 4. Okay? Now we want to show that K is a breakpoint. So it is a breakpoint. Okay, do we show a set of K points which H can shatter? Do we show that H can shatter any set of K points? Okay. Do we show a set of K points which H cannot shatter? Okay. Do we show that H cannot shatter any set of K points? Okay. Do we show that the growth function m of K is greater than 2 to the K? Okay, so now pause, answer, and if you're coming back, and if you said D, fantastic, you know how to show that K is a breakpoint. Okay, now let's take these. A and B are showing that H can shatter, okay, and those are moving not towards showing that it is a breakpoint, revealing the deficiency of H. They're moving towards showing that H is, able to conquer K points. In A you show that H can conquer some set of K points. In B you show that H can conquer any set of K points. Okay, a breakpoint is revealing a deficiency. You've defeated H. You've broken H. Okay. Now, a breakpoint is only a breakpoint if H cannot conquer any set of K points. If you show one set of K points, like we did with the perceptron and putting the points on a line, that's not sufficient to show that you've broken H, because you've just chosen a very peculiar set of K points. You have to show that you cannot shatter any set of K points for K to be a breakpoint. Okay. And if you even thought for a minute about E, then you really need to go and review last lecture, because, by definition, the growth function cannot be bigger than 2 to the K. Okay. It's upper bounded by 2 to the K. Okay. So E is just, it's not possible in any world where we've defined the growth function as a number of dichotomies on K points. Okay, let's get now back to the combinatorial puzzle, and let me first remind you, what was that combinatorial puzzle? Okay, so I give you 4 points, x1, x2, x3, x4, and I've shown here, 5 dichotomies on these 4 points, where the plane circle is a -1 and a filled-in circle is a +1. Okay, and the key fact about these dichotomies that we have listed is that if you zoom in on any pair of points, you will find that only 3 of the 4 dichotomies on that pair of points are listed. So let's, for example, focus in on, let's say x1, x2. So x1, x2. Let's focus in on x1, x2. and look at the dichotomies that we have. We have minus, 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 minus. So minus, minus is repeated 3 times. And then we have minus, plus, plus, minus. So the only 3 dichotomies that are listed on those 2 points are minus, 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 plus, plus, minus. Where's plus, plus? It's not there. Okay. And if you focus in on any pair of points, you will see a similar phenomenon that we haven't managed to implement all 4 dichotomies on any pair of points. And that's a constraint. And then the question was, what's the maximum number of dichotomies that you can add? Okay, now if you worked on this overnight or you thought about this from last lecture, and you realize that you cannot do more than 6, then you are correct. So 6 is the maximum. It's the maximum number of dichotomies that you can list on 4 points such that no pair of points is shattered by those dichotomies. Okay, and let's just see an example of what happens if we try to add another dichotomy. So now look what I've done. I've added minus, plus, plus, minus. And you can play around with this and add any dichotomy you want. Okay. And now let's look at the pair x2, x3. Okay, I've highlighted the pair here. And if we look, we see we've got minus, 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 minus. Okay, we've repeated minus, minus. Okay, now we've got minus, plus, plus, minus. Now we've got minus, minus, plus, plus. So we've got minus, 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 plus, plus, minus, plus, plus. So we have all 4 dichotomies, and we say that that pair of points is shattered. Okay, because all 4 dichotomies on those 2 points have appeared. Okay, so now what we're going to do, we're going to move to the board, and we're going to analyze this in a much more general setting where you can have endpoints, and we are not going to just restrict ourselves to focusing in on 2 points. We have endpoints, and we would like to zoom in on k points and require that no subset of k points is shattered. Okay, so let's attack this combinatorial puzzle. I've reproduced the 2 cases that we worked on from last time. So 3 data points, and you're not allowed to shatter any subset of size 2. You can list 4 dichotomies, but not more. And if you try, you will fail. Okay? 4 data points, you cannot shatter any subset of size 2. You can list 5 data points, but not more. Okay, so the max is 5, the max is 4. Okay, so now I'm going to introduce a notation. Okay, and anytime you introduce a notation, it pays to sort of read it slowly and make sure you understand it. Okay, so it's a combinatorial quantity, which I'm going to call B, and it's going to take 2 arguments. Okay, the number of data points. So this is the number of data points, n. Okay, so it's going to take as input n, and it's going to take as input k. Okay, now in this example, k was 2. So let me tell you what B of nk is. Okay, so this is so remember, the goal is to list as many distinct dichotomies as you can that did not shatter any subset of size 2. So B of nk is the size of that maximum list. So it's the maximum number of dichotomies you can list on, okay, and this is where n comes in, on n data points such that, okay, no subset of size k is shattered. Okay, so let's read this again, and let's read it slowly and make sure we understand. So this combinatorial quantity B of n and k takes as input the number of data points and the constraint. Okay, you must not shatter subsets of size k. And so B of nk is just the maximum number of data points you can list such that you do not shatter subsets of size k. Okay. So in this case, if we were trying to list the maximum, we're talking about B of, 3, because there are 3 data points, and we didn't want to shatter any pair of points, any 2 points, so B of 3 and 2. Okay, and in this case, we're talking about B of 4 and 2 again, because we don't want to shatter any pair of subsets, any size 2 subsets. Okay, and since 4 is the maximum, that means that this is the size maximum, this is the maximum list that you can construct, which on 3 data points, which does not shatter any pair, and this is the maximum list you can construct on 4 data points, so you don't shatter any pair. So B of 3, 2 is 4, B of 4, 2 is 5. Okay. Now, just for practice, let's work out some easy cases, and that'll also get us, to understand this definition. Okay. And since there are 2 parameters, let's list out B of n k in a table. Okay, so on the top, I will have k, so k, and on the left, I will have n. Okay, so k can be 1, 2, 3, 4, 5, 6, let us say, and n can be 1, 2, 3, 4, 5, 6, and so on. And so on. Okay, so let's first consider the case that k equals 1. So we don't want to shatter any subset of size 1. That's interesting. Okay. So if we don't want to shatter any subset of size 1, so let's consider n data points. And we'll do this for any n. So you have x1, x2, x3, up to xn. Okay, so we're interested in b of n, comma 1. Okay, so k equals 1. So k equals 1. So you can't shatter any subset of size 1. So let's list one dichotomy at least. Okay, so we list a dichotomy 1, let's say plus, and whatever. Now, if we're going to list another dichotomy here, okay, well, it must be different from this dichotomy that we already listed on at least one point. So let us suppose it's different on the data point x2. So that means on the data point x2, it's going to be minus. Okay. But look, this data point, both dichotomies on that data point are listed. So that data point is shattered. Well, this argument holds no matter which data point is classified differently in this new dichotomy. So it means I cannot add a second dichotomy, no matter how I chose the first dichotomy. Okay? Because I'm not allowed to shatter any subset of size 1. So it's a huge constraint. Okay? So B of n and 1, the maximum number of dichotomies I can list without being able to shatter any subset of size 1 is just 1. Okay? So when k is 1, the maximum number of dichotomies you can list is 1. It's a huge constraint that you are not allowed to shatter one dichotomy. Let's consider the case n equals 1. Okay, so B of 1 and k. Okay, well, B of 1 and 1 we have already computed. Okay, what about B of 1 and 2? Okay, so B of 1 and 2. B of 1 and 2. So the maximum number of dichotomies you can list on one data point, so you have x1, okay, such that no subset of size 2 is shattered. Okay, so let's list both dichotomies, so you can have either minus or plus. And I ask you to show me a subset of size 2 that's shattered. Well, you won't be able to because there's just no subset of size 2. Okay, so I can list these 2 dichotomies, okay, and no subset of size 2 is shattered. So this is 2. Okay, and if I had 3 here, there's no subset of size 3 that's shattered. And I certainly cannot list more than 2 dichotomies. So it's 2, it's 2, it's 2, it's 2, it's 2. In fact, B of n and n plus 1 is just 2 to the n. Because for the simple reason that on n data points, I can list all 2 to the n dichotomies. And there'll be no subset of size n plus 1 that's shattered just because there's no subset of size n plus 1. So, so I'm going to have 4, 4, 4, 4 here because 3 is bigger than 2. I'm going to have 8, 8, 8 here because 4 is bigger than 3. And then at 5, I'm going to have 16, 16. And at 6, 5, I'm going to have 32. Okay. So I can compute B of n and k for any k bigger than n. Interesting question. What about B of n and n? So how many dichotomies can I list on n points so that no subset of size n is shattered? Okay, think about this for a second. Now, I will point out to you that when you're talking about n points, x1 to xn, there's only one subset of size n, and you're not allowed to shatter that. So you can list all the 2 to the n dichotomies, but remove one of them, and you will not shatter that set of size n. So B of n is exactly 2 to the n minus 1. It's the number of dichotomies you can list on n points, so that the points themselves are not shattered. Well, if you shatter the points, you've listed all 2 to the n dichotomies, and if you're not going to shatter them, then you have to list at most 2 to the n minus 1, and you won't shatter any subset of size n. So let's now fill in this table a little more. So when k equals n, we have 2 to the n minus 1, which is 3, 2 to the n minus 1, which is 7, 2 to the n minus 1, 15, 31, and here we have 63. We've made some progress in filling this table. Nice. Okay, so let's be bold and go and try to fill in for general n and k. Well, it turns out we can do it, but instead we're gonna actually go after a bound, okay, because that's all we're gonna need for our purposes. Okay, so let's try to compute now. We've computed B of 4 and 2. Let's try to compute B of 4 and 3. Okay, so B of 4 and 3. B of 4 and 3. So we have 4 data points, and we're not allowed to shatter any subset of size 3. Okay. So imagine I have my 4 data points, x1, x2, x3, x4, and I'm going to try, and this number is certainly something. Okay, so B of 4 and 3 is certainly some number of dichotomies I can list, and that'll be the maximum. Okay. We may not know what it is, but it certainly exists. So let me list a bunch of dichotomies that fail to shatter any subset of size 3. So I'm going to start with all minus. Okay, I'm going to actually go after, let's say, 11, just for the hell of it. 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to list out 11 dichotomies. Okay, so all minus, then plus, 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 plus. So you see I'm listing them out in a systematic way. Plus, 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 plus. So I've listed out all the dichotomies, and you can see I've listed them out in a systematic way. I was very, very skillful here. I didn't list any dichotomy in which there are 3 pluses. Okay, and why did I do that? Because now I'm guaranteed that no subset of size 3 is shattered. Because let's consider any subset of size 3. For it to be shattered, we must certainly implement the dichotomy that's all 3 pluses on that subset of size 3. But that's not possible if there's no row with 3 pluses. Okay, so here is a list of dichotomies such that no subset of size 3 is shattered. And let us imagine that, we've listed the maximum, or, we don't even need to imagine that. Okay, the maximum such list has some length, maybe it's 11, maybe it's more, and it's going to look like this. It's going to be a list of dichotomies. Okay, and so let us just for the moment suppose that this list is a list for B for 3. Okay, so the list for B for 3 has to look something like this. Now what I'm going to do is I'm going to reorganize these dichotomies. Okay, I'm going to reorganize them in a very special way. So, x1. I'm not going to change the number. So you gave me this list that realizes B for 3, and I'm going to reorganize them. x1, x2, x3, x4. Okay, I'm going to reorder them. Okay, and in order to reorder them, I'm going to point out a couple of interesting things. So let's look at this dichotomy here, so which is plus, minus, minus, plus. So let's look at this dichotomy. Okay, I'm going to box it. And this dichotomy. Okay, and let's also look at, for example, this dichotomy. Okay, so we have 3 dichotomies here. Okay, and so why are these two highlighted in blue? Because look, if I focus on the first 3 data points, so I'm going to introduce a divider here to focus on the first 3 data points. Okay, you will observe that this dichotomy and that dichotomy have the same prefix on the first 3 data points. Plus, minus, minus, plus, minus, minus. Okay, so same prefix. In other words, the prefix is repeated. Okay. On the other hand, this guy, okay, so the prefix here is plus plus minus. Okay, so there's no plus plus, no plus plus, no, there's no other plus plus minus. If you look through here, there's minus 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 plus minus plus minus plus minus minus and so on. There's no other prefix in here that is plus plus minus. So this prefix in this list of dichotomies is unique. Unique prefix. Okay. So what I'm going to do is I'm going to separate out these dichotomies in a special way that's going to allow me to analyze, the structure in these dichotomies more easily. Okay. I'm going to start with the unique dichotomies. The unique prefixes. Okay. And then I'm going to list the repeated prefixes. But since if a prefix is repeated, okay, since the dichotomies must be different, then on the fourth data point here, they must be attaining different values. So every repeated prefix appears with +1 for x4 and -1 for x4. So I'll list the plus ones here and the minus ones here. So I will list the repeated prefixes. Okay. I will separate out the unique prefixes, and then I will list the repeated prefixes with +1, repeated prefixes with -1. Okay, so let's start with this unique prefix. So here's a unique prefix. Okay, so it's plus, plus, minus, minus. Okay, and this guy here, plus, minus, plus. So plus, minus, plus, with a minus. And this guy here, minus, plus, plus, with a minus. So minus, plus, plus, with a minus. These three are not repeated anywhere. If you look, you won't find this guy appearing anywhere. None of these three prefixes are repeated anywhere. Okay, so unique prefix. Unique prefixes. Let me call the size of this set, the number of unique prefixes, alpha. Okay. Now, let's consider the repeated prefixes. So, for example, here's a repeated. Let's do it systematically. So here's a repeated prefix with plus and minus. So we have, minus, 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 plus, and we have minus, 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 minus. So that's this guy and that guy. Then we have minus, minus, plus, minus. And here we have minus, minus, plus, plus. So we have minus, minus, plus, plus. Okay, so that's that guy. And we have minus, minus, plus. So we have minus, minus, plus, minus, minus, plus, with a minus. Okay, so that's that guy. Let's look at this guy here. There's minus, plus, minus, minus. So minus, plus, minus, minus. Okay, and where's this repeated prefix? It's right here. Minus, plus, minus, plus. So minus, plus, minus, plus. Okay, so that's that guy and that guy. And the guy we highlighted here, which is plus, minus, minus, minus. So plus, minus, minus, minus. Okay, and plus, minus, minus, plus. So plus, plus, minus, minus, plus. Okay, now observe. Okay, so let me again partition and focusing on the first three data points. These prefixes are unique. These prefixes get repeated. Okay, but one set has all plus at x4 and the other set has all minus at x4. Okay, now I want to emphasize that I didn't change the number of dichotomies at all. So this is still B of 4, 3. And I want to emphasize that this separation of dichotomies into these three sets is possible for any list of dichotomies. There'll be some set of prefixes that are unique and some set of prefixes that are repeated. And for any repeated prefix, it appears with plus and minus. Okay. Now let me call this, repeated prefix with plus, and this is repeated prefix with minus. Okay. So let me call this beta. Okay, so the number of these is beta, and since there are an equal number of repeated prefixes with plus as there are repeated prefixes with minus by definition, this is also beta. Okay. Now, by construction, B of 4, 3, B of 4 and 3 is equal to alpha plus 2 beta. So it's alpha plus 2 beta. I'm going to write this as alpha plus beta plus beta. Okay. And you'll see why in a minute. Okay. So first, I want to analyze alpha plus beta. Okay. And I'm going to ask you to focus on these dichotomies. Okay. So focus on these dichotomies. Well, we have 3 points. Okay. And alpha plus beta is a list of dichotomies on 3 points. Okay, so alpha plus beta is a list of dichotomies on 3 points. Or the box. Okay, alpha plus beta, restricted to the first 3 points. Okay. Alpha plus beta, let's say, induces. So all these dichotomies induce a list of dichotomies on 3 points. It's exactly these dichotomies. And in this set, there's no repeated dichotomy. So they're distinct. They are distinct. Okay? So that's the first observation. The second observation is, in this set of 3 points, there cannot be a subset of 3 that's shadowed by those dichotomies. Because if there were a subset of size 3 that's shadowed by those dichotomies, then the extended dichotomies on the subset of 4 will shadow those same subset of size 3. Okay. So there is no subset of size 3 which is shadowed. Okay, because otherwise, that subset of size 3 will be shadowed by the original list of extended dichotomies, and we know that no subset of size 3 is shadowed in the original list of extended dichotomies. What this means is that this list of dichotomies is at most B of 3, 3. So this list of dichotomies is at most of size B3, 3, because B3, 3 is the maximum list of dichotomies you can list on 3 points such that no 3 subset is shadowed. Okay, so what this means is that alpha plus beta is at most B3, 3. Okay, so this is at most B3, 3. Okay. Now let's look at beta. Okay. So let's look at beta. So let's focus on the prefix set of size 3, which is in general n-1. So let's focus on beta. This is a set of dichotomies. Okay. Supposing a pair of points is shadowed. So let's say that you will observe that no pair of points is shadowed. Let's consider this pair of points. On these dichotomies, you've got minus, 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 plus, plus, minus, and so you're missing plus, plus. Okay, so you'll observe that no pair of points is shadowed. And that's for a very good reason that no pair of points is shadowed. Because imagine if a pair of points is shadowed. Okay, so let's consider the dichotomies beta. Consider the dichotomies in this set beta. Consider beta. So, suppose that in this prefix list of dichotomies that are in beta, some subset of size 2, so 2 data points are shadowed. Suppose 2 data points are shadowed. And just for argument's sake, let's imagine that the two data points that are shaded are x1, x2. So they're not, but let's imagine that x1, x2 are shaded. So if x1, x2 are shaded, okay, let's consider the corresponding dichotomies in here. Okay, so now x1, x2 has all four dichotomies represented. Okay, and then all four will be represented in here because these two prefix sets are identical. So there'll be 4 here, but here those 4 are with +1, and here those 4 are with -1. So if a pair of points is shaded in this beta, that means that in this set of dichotomies, you know, if you augment that pair of points with x4, then those will be shaded by the original original extended list of dichotomies. So if two data points are shaded, then, you know, the full list of dichotomies, actually we just need the beta plus the beta. So the beta, the two betas, actually the two sets of size beta will do. Okay, so if there's a pair of points shaded, then combine that with x4. Okay, combine that with x4, and I'm now shattering 3 points. So if then the full list of dichotomies, okay, shatters those 2 points plus x4. Because here you would have your 4 dichotomies for x1, let's say x1, x2, your 4 dichotomies for x1, x2, and combine that with the plus minus. Here you get 8 distinct dichotomies that shatters x1, x2, x4. Okay. And that's not possible because we know that there's no subset of size 3 that's shaded in my original list for B43. So this is not possible. So what does that mean? That means that in this list of beta, when you look at the prefix dichotomies, which are dichotomies on 3 points, there's no 2 that are shaded. So this means that the prefix list, the prefix dichotomies beta do not shadow any 2 points. Okay. And what does that mean? That means that beta cannot be larger than B32 because you have 3 points and you're not shattering any subset of size 2. So this means that beta has to be at most B32. So beta is at most B32. So what have we proved? We have proved that B43 is at most B33 plus B32. Okay. Now, I just want to mention that this argument is basically generalizes to Bnk. Okay. So this is N. Okay, this is K, and you see this is N minus 1, this is N minus 1. That's basically because the argument was based on the prefix of size N minus 1. And here you have K, and here you have K minus 1. Okay. And so this argument generalizes, and actually you can sit down and work through it with N data points, no problem. Okay. You will find that Bnk is at most B n minus 1 k plus b n minus 1 k minus 1. And I'll box it. Okay. We've proved this recursion. Well, we illustrated the proof of the recursion for B43, and now you can sit down and complete the proof yourself. Okay? Now, that's interesting. Okay, so we've got an upper bound. It turns out that that this upper bound can actually be saturated, okay, and but we won't need that. Okay, it turns out that this upper bound is actually an equality, but we're not going to need that. Okay, so let me erase and let's see how this upper bound helps us. Okay, so how does this upper bound help us? Well, for one, we can use it to fill in this table, but not with exact values, but with upper bound values. Okay, so let's see what it's saying. It's saying is that if I'm at nk, then I go up 1 in n, and I look at that same value of k and 1 less in k. Okay. And I add those, and I get this value, and it's an upper bound. Okay. So I have here, so now let's write, upper bound on B N K. Okay, I'm going to use this recursion. So basically what we did is, and this is, very often the case when you analyze combinatorial problems, is that, you relate smaller problems to larger problems and you develop a recursion. And that's basically what we did. So, in this case, we go up and to the left, add, we get 4. So B32 is less equal to 4. Okay, B42 is less equal to, you go up and add, up and to the left and add those two, you get 5. And lo and behold, we showed that B32 is 4, and we showed that B42 is 5. Okay. And the upper bound says that we did, in fact, have the maximum. Okay. And what about B43? Well, you go up and to the right and add, you get 11, and I listed 11 dichotomies. So you cannot do better than 11. And you see that this upper bound is being realized, at least for these small cases. So it's an exercise for you, okay, to prove that our upper bound is actually realized, okay, but we're not going to need that. Let's continue filling. So this is 6, this is 7, this is going to be 16, this is going to be 26, okay, this is going to be 22, this is going to be 42, this is going to be 57, and so on. That's a bit tedious. Okay. And we're not typically satisfied, we're not completely satisfied with a recursion. When we solve a combinatorial problem, we'd like some kind of an analytical expression. Okay. So, theorem. Okay. B of n and k is at most, and it turns out that equality also holds, okay, is at most. So you can get equality. You can find an actual number of dichotomies that saturates the upper bound that I'm about to list here. So B of nk is at most the sum from I equals 0 to k minus 1 of n choose I. Now you might wonder, how the heck do the combinatorial coefficients, the binomial coefficients, pop into this analysis of this dichotomies and not shattering subsets of size k and so on and so forth? Well, this recursion kind of says it all, because this recursion should sort of remind you of the following very famous identity for binomial coefficients called Pascal's identity, which says that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. This is called Pascal's identity. Okay. So nk, if you want, you could call this binomial coefficient nk. So nk is equal to binomial coefficient n minus 1k plus binomial coefficient n minus 1k minus 1. The proof of Pascal's identity is not that hard. Think of it this way. This is the number of ways to choose k items from n. So you have n items and you want to choose k. So there are two scenarios. Either you choose the first item or you don't. If you choose the first item, you have to choose k minus 1. If you choose the first item, so you choose the first item, then you have k minus 1 more to choose from n minus 1. So there are n minus 1 choose k minus 1 ways if you condition on choosing the first item. And if you do not choose the first item, do not choose first item, okay, then you still have to choose k items from the remaining n minus 1, and so there are n minus 1 choose k ways of choosing the k items from the remaining n minus 1. And so the sum of those is the number of ways to choose k items from n, where you split it into two cases. You choose the first item or you do not. And so therefore, n choose k is n minus 1 choose k plus n minus 1 choose k minus 1. Pascal's identity. Beautiful. Okay. Well, you have this recursion, okay, and we claim this theorem, and using Pascal's identity now you should be well equipped with all your background in algorithms and discrete math and so on and so forth, that you should be able to prove this identity using this recursion and Pascal's identity. So you should be able to prove this upper bound. So prove using induction plus, recursion for B and K plus Pascal's identity. And the book has the proof, and the slides have the proof. Okay, and if you don't want to prove it, just take my word for it. It turns out that there are other interesting combinatorial, not combinatorial, but interesting mathematical facts. So theorem, okay, the sum from I equals 0 to k plus 1, to k minus 1 of n choose I is at most n to the k plus 1. Okay, again, you can prove this by induction, but now these are just, mathematical facts. The sum from I equals 0 to k minus 1 of n choose I is also less equal to, n times e over k minus 1 raised to the power k. Okay. The only reason I'm really showing you these bounds is to just make it obvious that this sum is a polynomial in n. Okay, because for a start, it's bounded by n to the k plus 1. So it's bounded by a polynomial in n. Okay, so the most important thing about these two theorems is that we have bounded, corollary, so what we have is that b of n and k, we could use is upper bounded by this guy, or it's upper bounded by this guy, it's upper bounded by that guy. So we have many different choices for, the functional form of the upper bound on b and k. Okay, and the one that I'm going to use is, n to the k plus 1, the simplest looking. Okay, so we proved that b of nk is less equal to n to the k plus 1. Okay. And let me remind you what this b of nk is. It's the max number of dichotomies on k points, on n points, such that no subset of size k is shattered. Okay, so this is what we have proved for this combinatorial problem, where we define this combinatorial quantity b of nk. Okay, and I repeated the definition of b of nk. It's the maximum number of dichotomies on n points, so that no subset of size k is shattered. And if you fell asleep for that whole derivation, okay, we basically proved it rigorously, although I left some steps for you guys to fill in. But if you fell asleep, it's time to wake up, okay, and understand carefully this definition, okay, and the fact that we have proved that this guy b of nk is at most n to the k, okay, plus 1. But basically it's at most n to the k, roughly speaking. It's polynomial in n. Okay. Polynomial in n. Okay, so now I'm gonna now switch gears, because by now you've lost patience with me. You're thinking, what? This is not a class in combinatorics. Okay, and that's why I told you, if you're not interested in the combinatorics, fine, but at least appreciate what we have proved. Okay, we defined a combinatorial quantity and we proved an upper bound on it, and it's time to wake up, because now I'm going to link this combinatorial quantity, which was related to that puzzle. I'm going to link this combinatorial quantity to learning. In particular, I'm going to link this combinatorial quantity to the growth function of a hypothesis set. Okay, so let me erase, and we'll be back to make that link. Okay, so, this has been a relatively mathematical lecture so far, and it's now time to reap the payday. It's time for the big miracle of the day. Okay. We're gonna relate this abstract combinatorial quantity, b and k, to learning. Specifically, we're gonna link it to the growth function of a hypothesis set. Okay, and I mean, this is just beautiful. And it's a very short link to make. But before I go and make that link, let me remind you, the last lecture we talked about growth functions and we computed it for some hypothesis sets. Okay, so we did the 2D perceptron, the 1D positive ray, and the 2D, rectangle, the positive rectangle. Okay, this was the axis-aligned positive rectangle. Okay, and then for various n, okay, so for n equals 1, 2, 3, 4, 5, and let's say 6. Okay, we computed m sub h of n. Okay. Now for the 2D perceptron, it was you can shatter 2 points, you can shatter 1 point, you can shatter 2 points, you can shatter 3 points. Okay, so 8 and 4 points. No set of 4 points can be shattered. So this was 14. Like, the crucial thing is that it's less than 2 to the n. So let me put 2 to the n here. Nice lines. Okay, so 2 to the n is 2, 4, 8, 16, 32, and 64. Okay, so that was the 2D perceptron, and then 5, it's going to be less than 32 because you can't implement all the dichotomies on 14. 6 is going to be less than 64 and so on, but we didn't compute those. Okay, for the 1D positive ray, we actually computed the growth function. It was equal to n plus 1. Okay, so n plus 1 is equal to 2 here, and here it's already 3. Okay, and so we have identified a deficiency of this infinite hypothesis set already at 2 data points. So the positive ray cannot shatter 2 data points. So there's some dichotomy it cannot implement, but and that's easy to figure out. So remember the positive ray. At some point, it's positive to the right. So if you have the dichotomy plus minus, it cannot implement it, because to implement the plus, you've got to put the threshold to the left of the plus, and then everything is going to be plus, including the minus, which means it cannot implement plus minus. Okay. So already at 2 data points, there's no set of 2 data points which can be shattered by the 1D positive ray. What that means is it's deficient. Already its deficiencies are sort of showing up at 2 data points. We say that n equals 2, n equals 2 is a break point, and n equals 4 is a break point. Remember, we had this practice with breakpoints. Okay, the 2D rectangle was more interesting. Okay, so here we actually computed this. It was 4, 5, 6. So this is an example where we could actually compute. Okay, and the 2D rectangle was 2, 4, 8, and things were looking good until we got to 5, where we didn't compute the growth function. We proved that it's less than 32. So less than 32. So I'll put it in red. Okay. Less than 32. In other words, it's broken. Okay, and that's interesting too. Okay, so all the uncountably infinite hypothesis sets that we try get broken at some value of n. In other words, there's no set of 4 points, there's no set of 2 points, there's no set of 5 points that those, respective hypothesis sets can shatter. Okay, so they're deficient. We've identified that they're not as complex as one might have thought by just looking at how many hypotheses there are in there. Okay, so the growth function, let me remind you again the definition. The growth function, m sub h of n, for the hypothesis set n, is equal to the max number of dichotomies that can be implemented on n points. And you get to pick those n points. You're trying to maximize the number of dichotomies. So let us suppose that your hypothesis set, like all the ones we tried, has a breakpoint. So there's some value of n that breaks it. So let k be a breakpoint point for h. Okay, so what does that mean? No set of k points can be shattered by h. Okay. And now let us consider M sub h of n. It's a list, it's the maximum number of dichotomies that the hypothesis set can implement on any set of n points. So let us suppose that that maximum number of dichotomies is realized for the set of points x1, x2, x3 up to xn. So on this set of points, if I go through all the hypotheses in H and list all those dichotomies, so I'm going to have a dichotomy here, plus, 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 maybe plus, maybe I can implement all the plus, and then plus, minus, plus, and so on. I list all the dichotomies. I'm going to get M sub h of n dichotomy, because this is a set of points that realizes that maximum potential of h. Okay. And now remember, well, let's consider the case where n is greater than k. Okay. Or n is greater equal to k. So now let's consider any subset of size k. So consider any subset of size k. Subset of size k. And I ask, if we look at if we focus in on those k points and look at these dichotomies on those k points, I claim that those k points cannot be shaded. Because if they were shaded, then k would not be a breakpoint. So, any subset of k points is not shaded by these M sub h of n dichotomies. Okay. And why is that? That is because k is a breakpoint. And so there's no set of k points that can be shaded by the dichotomies in H. And these are the dichotomies in H on those k points. Okay, so it cannot be shaded. Okay. So that means I've listed some dichotomies. Okay, they're all distinct, and for these dichotomies, no subset of size k is shaded. But B of nk is the maximum list of dichotomies that are possible, period, on any n points, such that no subset of size k is shaded. This may not be the maximum, because these are just the ones that came from H. Okay, so these are the special dichotomies that H implemented. Now, you might be able to add more dichotomies to this list without shattering any k points. It's just that those other dichotomies you can add are not implemented by H. But whatever H can implement, we know that, B and K is the maximum number of dichotomies you can list on n points, so that no subset of size k is shaded. Okay? So what we know for sure is that this list cannot be larger than B and K. So, M sub h of n is at most B and K. Voila! That is the link. This combinatorial quantity gives us an upper bound on the growth function for any hypothesis set that has a breakpoint K. So now let's state it as a theorem, full-fledged theorem. And it is worthy of a theorem. So we have proved the following theorem. Let H be any hypothesis set. Any hypothesis set. Okay. Then, one of two things is true. Either H is so complex, for example, H is every possible hypothesis on Earth, in which case it will be able to shatter any set of n data points for any n. Well, okay. As long as those data points are distinct. So if H is any hypothesis set, then one of two things happens. Either, okay, bullet point. H is so complex that it never gets broken. So no matter what n you give me, I can find a set of n data points with which H can shatter. Now, it turns out that you can get H's that have this property, even that are not as complex as every possible hypothesis set. And you can see some of the problems for some details. But, so H is so complex that it never gets broken. So you can find n data points which it can shatter for any n. In this case, m sub h of n is equal to 2 to the n for all n. Okay? That's the definition of H never gets broken. Its growth function is always 2 to the n. Remember, this growth function, if we succeed in putting it in the error bar, is of no use to us. Okay. Or, while H may be, let's say, infinite in size or uncountable or what have you, for example, like these hypothesis sets, so, or H does get broken. So that's the second case. H does get broken. In which case H has a breakpoint. It has a breakpoint. Let's call it K. So for example, in this case, the 2D perceptron has a breakpoint 4. The 1D positive ray has a breakpoint 2. And the 2D rectangle has a breakpoint of 5. Okay. And if it has a breakpoint K, then we just proved, then m sub h of n is at most b of n and k, which is at most n to the k minus 1 plus 1. There's a typo here. This should be k minus 1. K minus 1. This should be k minus 1. K minus 1 in those bounds. Okay, so theorem. Okay, so this means that the breakpoint for H plays an important role in bounding m sub h of n for all n. So let's see what that bound looks like in each of our 3 cases here. So, bound. What does the bound look like? Okay. So, in this case, for the 2D perceptron, the breakpoint is 4, so k minus 1 is 3, so less equal to n cubed plus 1. The breakpoint is 2, so is k equals 2, so k minus 1 is 2. Sorry, k minus 1 is 1, so less equal to n plus 1, n to the 1 plus 1. And that, in this case, is achieved, because we computed it exactly as n plus 1. And in this case, the breakpoint is 5, so less equal to n to the 4 plus 1. Okay. Now I just want to pause and let this sink in. And now I'm going to interpret this for you. Okay. The first and most interesting sort of conclusion is there are 2 kinds of hypothesis sets. So if I plot, on this axis n, and on this axis, let us say the log base 2 of m sub h of n. Okay? I'm plotting the log base 2 of m sub h of n. So, so that this exponential is not just exploding. So the log of this guy is n. Okay? So this is no break point. Okay? And I'm going to call this bad. Why bad? Because if indeed m sub h of n functions as an effective number of hypotheses in our error bound, well then this is of no use, so it's bad. the error bar doesn't drop to 0, and so, you'll never get into a situation where E in is close to E out. Then there's the other case where H has a breakpoint, in which case, the log of the growth function, because remember, it's the log of the growth function that would appear in the bound. Okay, so in this case, it's growing linearly in n, and then when you divide by n, it's a constant, and the bound doesn't shrink. In this case, when you take the log of the growth function, it's at most, a constant k times the log of n. Okay, so breakpoint. Okay, so two interesting things. This logarithmic behavior is the same bound for any hypothesis set, and they can come from different domains, different problems, different whatever. Any hypothesis set, as long as it has a breakpoint k. Any hypothesis set. Any hypothesis set, as long as it has a breakpoint k. So the bound on the growth function, the bound on the complexity, just depends on the breakpoint. Okay? So that's the first interesting observation, that all hypotheses that have the same breakpoint are sort of bunched together. They all have an equal complexity. So you can think of this breakpoint as in some way capturing the effective complexity of a hypothesis set. But the other observation is also very interesting. Okay. So there's the logarithm of the growth function growing linearly. There's the logarithm of the growth function going like log n. There's nothing in between. So you might ask, well, what about, square root of n? So 2 to the square root of n for the growth function. Okay, no, not possible. So you can think of this as good, because remember we argued that if we put log n over n in that error bar, if we put the logarithm of this in the error bar is going to shrink to 0. So E in will approach E out. So that's good. But if you think about this as ugly, there are good hypothesis sets whose growth function grows, logarithmically, whose log growth function grows logarithmically in n. There are bad hypothesis sets whose log growth function is growing linearly in n, so that are bad. But there's no ugly. There's no ugly. There are no ugly growth functions. There's only good and bad. It's a dichotomy. Okay. And what this tells us is, and for example, these are all good hypothesis sets because they have breakpoints, and so their complexity, their effective complexity, when you take the logarithm of the complexity is growing logarithmically in n, albeit there's some constant which is related to the breakpoint that's multiplying the logarithm, but it's still log n over n. So if you take n to infinity, the error bar goes to 0. Remember the error bar. The error bar, E out, is less equal to E in plus order of log, the size of the hypothesis set divided by n. And our goal, okay, is to, replace the size of the hypothesis set by this effective complexity. Okay, and then we argued last time that replacing it with the effective complexity is useless. It's not going to help us in getting E in close to E out if this effective complexity is always 2 to the n, the upper bound, the trivial upper bound. And what we have seen now is that, if ever it gets below the trivial upper bound, it's going to be polynomial. That is a miracle. That it's for example, you might have guessed maybe 2 to the n minus 1 is possible. It's always 1 less than, the maximum number. Not possible. So when we say breakpoint, even if you get 1 less than 2 to the n, that's a breakpoint, and that immediately crushes the hypothesis set to being polynomial growth function, or if we take the logarithm of that, which we're anticipating putting into the error bar, the logarithm of that is log n. Okay. And so this error bar will go to 0. Okay. So if we succeed in replacing the size of the hypothesis set with the log of this effective number of hypotheses on a data set of size n, then the conclusion is startling. There are 2 types of hypothesis sets. There's the hypothesis set that's bad, for which this error bar doesn't go to 0, it stays large constant, in which case these bad hypothesis sets, you cannot get E in approximately equal to E out, which means you cannot implement the first step in learning. Okay, and there are these good hypothesis sets, the good ones which at some point get a breakpoint. Okay. And once you have gotten a breakpoint, if we can, put the growth function in here, then this error bar goes to 0 as n goes to infinity, and at least in principle, as n becomes large enough, it's possible to accomplish the first step of learning. And now we have already agreed between you and me that the learning problem is feasible when we view it as this two-step process. Step 1, get E in close to E out. Step 2, get E in close to 0. Okay, and you have to implement step 1 theoretically. So what does that mean? That means that when you approach a learning problem, you can only use a good hypothesis set. Okay. One for which you can get the error bar down to 0 and get E in close to E out. So there are good hypothesis sets for learning and bad hypothesis sets for learning. Okay. So our main goal for this lecture was to establish that we can indeed, show that this effective complexity, this effective number of hypotheses, the number of hypotheses when viewed through the lens of a data set of size n, so this effective number of hypotheses is at most a polynomial in n. It's a huge step. The next step is we need to show that, can we replace the size of the hypothesis set in here with this effective complexity? So the details are in the textbook, and I'll just give you the rough idea of how that happens, and then I will state the bound, which has the size of the hypothesis set replaced by this growth function. And then we will be done with this part of the theory that establishes that it is possible to learn with infinite hypothesis sets, providing that the hypothesis set you choose to learn with has a breakpoint. Okay, so what did we prove? Our main goal so far in this whole mathematical lecture is ultimately to show that even for infinite hypothesis sets, uncountably infinite hypothesis sets, this growth function does not remain 2 to the n. As long as that hypothesis set has a breakpoint, as long as it can be shown to be deficient for some n, its growth function is bounded by a polynomial. Polynomial is good because that will result in the error bar shrinking to 0 and give us E in approaches E out when n becomes large. Okay. So what remains is to show that we can indeed replace the size of the hypothesis set in that error bar, in the generalization error bar, by this effective number of hypotheses, which is the number of hypotheses that can be implemented on a data set of size n. Okay. So the challenge here is to link to E out, and I'm not going to give you all the details. You can see all the details in the text, okay, and the rigorous proof of the final bound that I'm going to show you. I'll just sketch for you the very high level ideas. Okay. So the first challenge is to link to E out. Okay. Now you have E out for G and E in for G. And the key insight here is that if you were to generate another sample of data, okay, and compute the error of G on this other sample, we can call this other sample, it's typically called a ghost sample, we'll call it a data set prime. Okay, and if you evaluate on this data set prime, you get another in-sample error. But now that data set prime, G was not selected for that data set prime. So this E in prime, will be close to E out, related by the sort of single hypothesis Hofstede bound. Okay, and so in this picture here, where you see this probability distribution that looks a little bit like a Gaussian. So let's consider the situation where E in deviates from E out. Okay. And so we're interested in bounding the probability that E in deviates from E out by a large amount. Now let's look at what's happening with E in prime. E in prime is just another data set, and when you evaluate, it's like a test data set in some sense. And when you evaluate G on E in prime, it's going to oscillate. It's going to oscillate around E out. In particular, half of the time you're going to see, roughly half of the time you're going to see an E in prime that's less than E out. So in some sense, the probability that E in is deviating from E out by epsilon is approximately a half the probability that E in deviates from E in prime. Okay. And so there's the link. The probability that E in deviates from E out is approximately half the probability that E in deviates from E in prime. Okay. And so now we have linked E out to E in prime on another finite data set. Okay? And so all we have to do is analyze the deviations between these two in-sample errors. On one of the samples, you picked G from the hypothesis set. On the other sample, you just think of it as you're just testing. Now, the complication that arises is that when you have these two samples, you actually have two endpoints. So, in this little example here, you've got x1, x2 up to xn. Think of that as D, and then D prime has these additional two endpoints. And so we really need to look at what your hypothesis set, how many functions your hypothesis set can implement on all these two endpoints. Okay, and so that means that we need to analyze the growth function for 2n. But no problem. If the growth function for n is polynomial, so n to the k, then the growth function for 2n is 2n to the k, which is 2 to the k. That's a constant because the breakpoint is a constant number k. So it's just 2 to the k, n to the k. So it's just a factor of k. It doesn't affect the polynomial nature. Okay. So basically, up to technical details, okay, which I'm ignoring here, and you can find in the text, ultimately everything boils down to analyzing a hypothesis set of size, of effective size m sub h of 2n. Okay, and when you collect all these technical details together with the insight that to compare E in to E out, it suffices to compare E in to E in prime. Okay, we get the generalization bound that we want. And this generalization bound is so famous that it has a name. It's called the Vapnik-Chervonenkis bound, or the VC bound. And I'm just going to, we can go through the probabilistic version, but I'm just going to go through the, the error bar version, which they're all equivalent. Okay, but the error bar version might be a little bit easier to parse. Okay, and so for infinite hypothesis sets, okay, it is always the case that, the following bound holds with high probability. Okay. So with high probability, E out is less equal to E in of G plus an error bar. So it's the same basic bound that we had before, the same basic error bar, except, up to some constants which were 1 over 8 now becomes 1 over 2 now becomes 8, and 2 now becomes 4. Okay, so up to these constants that changed, you have replaced the size of the hypothesis set by the growth function at 2n. The 2n came from the 2n data points. Now, it's possible that, m sub h of 2n is 2 to the n for all n, in which case that's a bad hypothesis set, and this error bar does not drop to 0. And you cannot learn from this hypothesis set because you cannot implement the first step of learning, which is that E in close to E out. On the other hand, for good hypothesis sets, this error bar drops to 0, and we have established, in principle, the first step of machine learning, which is that with sufficiently large n, as determined by, what's your error tolerance and what's your probability tolerance and what's the growth function, okay, for sufficiently large n, what's the breakpoint more specifically. For sufficiently large n, the error bar goes to 0, E in goes to E out. First step of learning accomplished. Sayonara.